Everybody, this is Greg Mefford from Bleacher Report. He's going to be talking to us about open telemetry.
All right, thank you. I'm excited to be talking to you today about OpenTelemetry. This is kind of something in the observability space that I'm very excited about. And as I was preparing for this talk and kind of doing some rehearsals and talking to people about it, they were saying that they got excited about it too. And I hope that that's what happens today. So to get started, I want to talk a little bit about what is OpenTelemetry. But first of all, what problem are we trying to solve with OpenTelemetry? As Justin was just talking about, as we're building bigger and bigger things, more complicated things, bigger business problems, a lot of the issue that we have is like our engineers don't even know how these things work. So the observability problem is like, how do I observe what this thing is doing so that when it stops doing the thing I expected, I can figure out what to do about it. So you might be familiar with this process. If you press the button, you receive the bacon, right? But what if you don't get the bacon when you press the button? So we're going to science the situation. Let's start with what we can see. So first of all, no bacon. 0 out of 5 stars. Like, this is terrible. Would not buy again. There's warm air coming out. I don't know why there's warm air coming out. Is this supposed to be like cooking the bacon? That doesn't seem safe. I don't know. There's lots of noise coming out of this thing. Yeah, I don't know what's going on. Okay, the noise stopped. No bacon. So yeah, definitely broken. But if I engage my famous silver lining machine, it did respond to inputs. I pressed the button. It did something. Like, it was trying to give me bacon and it did not give me bacon. So observability. A lot of your vendors, when you ask them what observability is, they will tell you that it's logs, metrics, and distributed traces. I want to refine that a little bit and say they're not really pillars. They're more like aspects on your system. And in the way that the different faces of a cube have aspects that are related to each other, they also have aspects that are kind of orthogonal to each other. So if you look through your system in the distributed tracing sense, maybe you can see how long a particular request took, or you can see, like, did it have an error? What was the error? But if you aggregate those traces over time or over some kind of data point, you can see, on average, my requests are taking this long, or at the 99th percentile, they're taking this long. In addition, so your distributed traces, you might see that there's a stack trace or an error. You could also collect those in a logging system, and you could see how many of those you have of different types. Or maybe you have some auditing requirements where you have to say, this thing happened. It wasn't an error, but we have to keep track of when those things happen. So observability, I see it as different aspects of your system, different stories that you may want to tell. So distributed tracing tells a story, as I mentioned, about particular requests. They're usually aggregated by tags and data. So usually tags are things that are used for filtering, for example, successes or failures. And then metrics tell you a different story, usually about types of operations, right? And they're aggregated over time and over tags, similar to traces. So for example, you might say that you had 500 pieces of bacon dispensed successfully in the past hour. So like examples of, there's usually a number involved, it's usually some type of a thing, and then a tag might be that it was successful. So logs tell you a different story in very fine detail. Ideally, they're structured and not just like a human prose sentence about what happened. So like key value pairs would be a good idea. They're usually collected centrally and indexed so that, for example, the problem we're trying to solve with logs is I have 1,000 servers that are all doing things. I want to look in one place to see those things. So here's an example, key value pairs. Bacon jam detected. That's an error result on the dispense action, right? And then ISO 8601, the only correct timestamp format. Yeah, that wasn't a joke, but good, I'm glad you got it. So one of the things, as I'm talking about observability and distributed tracing in particular, a lot of people, they're either just getting from the logs to metrics transition, so they're just trying to start having like statsd or Prometheus or something like that, aggregating their data over time. But they're not really familiar with what distributed tracing is for. Like, how do you do this? What is it? How do you use it? So I want to talk a little bit about what that is. So there's this concept of a span, right? And it's kind of what you would expect. It's something that happens over a span of time. So there's a start time, there's an end time. It has a name usually to tell you what was happening during that time. And a span also can have attributes. So this is where your tags and your metadata come in. They also have a parent-child relationship. So if you're a manager in the audience, you might say that this is a Gantt chart or waterfall chart, flame graph if you look at it upside down. So the idea here is that each span knows what its parent is. So the Phoenix endpoint calls into the Phoenix router, calls into the Phoenix controller, and then the controller can do various things, including render your views. Each span also knows what trace it belongs to, and that's just used to group these things together. The top level thing doesn't have a parent, so that's just a root span. This is kind of an example in Elixir systems. We have a lot of concurrency, right? So somehow we have to model that these things happened at the same time, but they're not related to each other as far as parent-child relationships go. So in this case, we have a controller that's doing two HTTP calls in parallel. You can see that just because they're not touching each other. That's one way you can draw that. But then each of those downstream HTTP calls is going to potentially call into a different service. And that's kind of modeling going over the network to some other thing or some different Elixir process. So sometimes those end up getting colored with a different color. But then they all belong to the same trace, right? They need to somehow propagate the fact that they belong to the same trace and what their parent was. So here I'm showing that the different colors represent different servers that these actions took place on. But we need to propagate that so-called span context between the servers. The span context has a little bit of state associated with it, but also whether or not we're sampling this trace. And I'll get a little bit into what sampling's for later. This used to be sort of a Wild West thing where each vendor would invent their own HTTP header that was incompatible with all the other ones. And as you can imagine, that was amazing. So OpenTelemetry is solving that, not directly, but by using this thing that the W3C has organized to standardize that process. So basically, the upstream server sends the span context down to the downstream server, but it doesn't need to worry about what that downstream server is doing other than the response that it normally gets back. Similarly, the downstream server doesn't know what the upstream server was doing other than here's the parent span that I belong to, so that we can stitch these things back together later. To be more specific, you don't have to pass all the tracing data down to the server. You don't have to pass all the tracing data back up to the server. It's just like a pointer. And then the collector's job is to take all those things from all those servers and stitch it back into a meaningful trace. So the collector's other job is to determine which ones of those things we're going to keep, because obviously you need to pay your vendor based on how many of these things you have, right? So you don't want to keep all of them. And also, we're humans and we can't look at all of them. So you have to sample them down. There's this concept of head sampling, which is at the beginning of the trace, we just kind of flip a coin, make a random decision, are we going to keep this thing or not? That has a lot of benefits because in the case of the top one, we spend a lot less resources because we know we're going to throw it away anyway. But we still do need to do a little bit of propagation of context so that things stitch back together properly. Basically, you need to communicate down to the other server, don't trace this thing because I'm not tracing this thing. There's also a concept of tail sampling. So that's once you get to the end of this process, you might decide, really we only want to keep the ones that have errors in them or the ones that are long requests, things that like a human will actually want to go look at. So I want to digress a tiny bit and talk about what the Beam has for built-in tracing, because this is not used for distributed tracing, and that's often a tripping point for people. So Erlang gives us this trace pattern built-in function, and if you were going to use that, you would probably use recon trace. So if people are familiar with that thing. The way that works is that the Beam has a singular trace process that's available, and you can tell it, I'm interested in these patterns or these things. So then whenever your application processes perform those actions, they kind of send magic messages to this trace process, and then it sends you regular messages that you can consume. So the good things about this is it's production safe. This is something that's not just for development. You can do this on your running Beam releases. It's for interactive troubleshooting and debugging. But the problems are that it's one per beam, so there's only one trace process per beam, and it's also local only, so it doesn't help you with distributed tracing. So that's why we don't use those for distributed tracing. Okay, so I want to talk a little bit about what observability superpowers you get with distributed tracing. The first being single request flame graphs. So I'll give you an example. This is from an example project and using Datadog APM. So in this example, you can see that there's a plug-based gateway that's calling into a Phoenix-based backend, and then the Phoenix-based backend is calling into Ecto. So like, without seeing any of the words on the screen because they're tiny, you can kind of get a feel for what's the shape of your application, even if you didn't write it. You can also get stack traces in context. So this is an example this is not from an example, this is from an actual production system where you might be able to see that towards the bottom here there's a red box that's outlined, and that means that there was a stack trace there, but then the top level result was 200. So you can drill in and you can see what was that problem, undefined module, that doesn't seem good, but somehow we handled that and we didn't crash at the top level. So like if you were collecting error metrics, you might say, wow, we had like 1,000 of these and that's not good, like we need to go fix that right away. But actually, like we're recovering and we're handling, and it wasn't a big deal. Another thing you can see right away is N+1 queries. This is definitely an example, not from production at all. So yeah, like just as you zoom in, you can see that each of that blur of blue was an ecto call. So like, I guess the meta takeaway here is it's not just for N+1 queries, but maybe you can see something problematic structurally in your application, like database queries from the view, or just, even if you didn't write the code, you can easily visualize that. Another thing you can easily visualize is downstream calls to the same service. So in this example, you have a top-level application, and it's using all the tools we have available to us in Elixir. So like, streams and maps and enums. You can easily make a lot of downstream calls in parallel. But in this case, you can see that there's 3 calls to the same service based on the color. And maybe we could combine those and it would be more efficient. On the other side of that coin, maybe you can have an async opportunity where you're making a downstream call and then you're using the results of that to make another downstream call. Maybe you could make a smaller call and just get some IDs and then make the 2 downstream calls in parallel. So like look into those things, I guess. Something else you can see visually is network latency. So in this case, we're making downstream calls to a service, but there's big gaps here, right? So like what accounts for the gap between making the call and the downstream thing working on the call? I'm not saying it's all network latency, but maybe a lot of it's network latency. I think last but not least, like probably least, like this is probably the most important thing, is at Bleacher Report, when we started to do this distributed tracing thing, it was a huge culture shift for us from gut feel and metrics and logs to here's a trace of exactly what happened. Like it was very different when you can just email someone a link to a trace and they can open it up. Distributed tracing pitfalls real quickly. Make sure you're doing some kind of sampling. As I mentioned, the vendors will charge you. So sample the things to only the traces that you're going to look at. Incomplete traces is something that you can stumble into really easily. If you don't propagate the fact that you're tracing something or not tracing something, then you end up with the downstream service thinking that it's not part of the upstream services trace. So you don't see it in the upstream services trace, and also you get like a lot more traces in general. Clock skew is an interesting problem to be aware of. It turns out even if you're using NTP, the clocks on your servers are not going to be the same exactly. So in this case, our downstream service predicted ahead of time that we were going to call it, so it started working on it for us, save us a little bit of latency, right? No, like in fact, the clocks are wrong, and like that belongs somewhere in the middle, but it's hard to know where. All right, so just at the end of the talk here, so OpenTelemetry is a merger of Open Census and Open Tracing. So I want to talk a little bit about what each of those things are. So Open Tracing is a CNCF project, and just from their website, it's not something that you can download, and it's not a standard. So I guess you might ask yourself, what is this? And I think it's more of like a pirate code of guidelines and things that people have like worked on to solve this problem, but it's not actually like an API. It's not an API spec. It's various implementations that people have actually built. So the project that I work on is called Spandex. It implements this spec or guideline. There's also Otter, which is an Erlang library, and then X-Ray wraps around that Erlang library. Something interesting from the open tracing community is that they got this built into Nginx as a proxy. So like that's kind of an interesting idea that like middleware vendors could build this technology into their thing and transparently trace through it. And I think we need to see more of that. So the competing standard there is Open Census. You'll see that it is a single set of libraries, and it's about metrics and traces, whereas Open Tracing was only about traces. And they also had plans to add logs in the future. Open Census was sponsored by Google, and Open Tracing sponsored by CNCF, and now they're merged together, and CNCF is sponsoring this joint project. So OpenTelemetry is a single set of libraries and tools, as you might expect. They've fixed that problem. It's also metrics and traces and also logs in the future. So it's like an overall observability tool. And I think really the most exciting thing for me coming from the Veeam ecosystem is that this is from their website. Like this is opentelemetry.io, and Erlang is listed there. And we're like actually a thing. People remember that there's Erlang in the world. So as I mentioned, I work on the Spandex project. We have easy integration with Phoenix, Plug, and Ecto. We implement open tracing. On the downsides, we only support Datadog APM, and also a lot of it's written in Elixir macros, so that makes it hard to use from Erlang. Conversely, Open Census obviously implements Open Census. It supports various trace collectors, including Datadog APM. But being written in Erlang originally with Elixir like layer on top, it makes it easy to use for both. So the strategy that we used on the Veeam ecosystem side is the same as in the industry. We're taking these two teams, merging them together, and now we have official OpenTelemetry Erlang. And the description here is that there's an API that doesn't actually do anything except provide an integration point that libraries can use. And then there's an SDK that actually makes things work. So if you're not planning on using OpenTelemetry, libraries can still use this API, and it's like a no-op, so it's not adding much code. I want to talk really briefly about telemetry for metrics and events. And just a shout out that Samuel's going to be talking in more depth, I presume, about this. And I'm looking forward to that talk. But all I want to tell you about telemetry is that it's simple, it's standard, and it's like fairly safe, like as safe as anything is. So in terms of being simple, the way telemetry works is that in your libraries, you can call execute, and that will fire off an event that can have metrics in it. And then in a receiver, you can attach to those events, and you can handle them however you want to. So this is how you would handle those events, either in Elixir or Erlang. It's pretty easy. It's just a callback that gets called. Something to note here is that they're called synchronously, and that's really important for distributed tracing, where if you have a start event or a stop event, you want to be able to know when that happened, not divorced from the actual process of it happening. Yeah, so like I mentioned, there's start and stop events that you can use as tracing hooks. It also has time series metrics attached to those events, so that makes it really easy to aggregate and report those up. This is a simple piece of example code where we're showing like the recommended way that you would integrate telemetry into a library. So you'll see there the lines that have the red telemetry module on them, telemetry.execute. You give it some event name, and then we're recommending that you use start, stop, and failure to describe that you're starting an action, stopping an action, and then if something crashes, you emit a failure event. And then you'd probably want to re-raise here at the bottom, but that's kind of up to your library. All right, so it's pretty simple. And the way that it works is that telemetry has this ets table where it manages each of the handlers that exist. If any of them crash as they're going through and iterating synchronously, they get removed from the table. And then so just like American baseball, it's one strike and you're out. So it's pretty safe. So this is kind of like a quick checklist. I'm sure there's other ones, but these are some popular libraries that are already using telemetry. So we're just missing your library, and then we'll be all done. So it's pretty standard. And my key takeaways, just in general from the talk, is look into OpenTelemetry for your apps, because telemetry is more like emitting the events, and then OpenTelemetry will take care of the rest of getting it to whatever vendor you're choosing. OpenTelemetry is almost ready at this point, and telemetry itself is ready, and it's already being used. So that's all I got.